Hello everyone! Ripple has been doing well in the markets recently, but I still see a lot of confusion about its fundamentals, so this is part 1 of a series on the fundamentals of Ripple. Let's discuss algorithms. You probably know that Bitcoin uses the blockchain algorithm. Without getting too technical, let's discuss briefly how Bitcoin works. Alice wishes to send 1 Bitcoin to Bob. To do this, she signs a message and enters it onto the Bitcoin network. This message effectively is a deed of ownership for that coin. By signing it, Alice renounces her rights to the coin and Bob obtains ownership of the coin. So far so good, but how does Bob know that Alice had the right to transfer him the coin in the first place? Well, it's quite simple. Bob can look up all previous owners of the coin and trace the chain of ownership from the first owner to Alice and then finally to himself. So just how many transactions are we talking here? Well, let's try not to get too scared by the math, but basically the number of transactions on the network is always going to be the number of users on the network multiplied by the number of transactions each user makes. The number of transactions each user makes varies from network to network, however empirically we know it tends to fall between the logarithm of the number of users and the number of users itself. So that makes what's called the storage complexity of the blockchain algorithm somewhere between n log n and n squared. What do these terms mean? This graph illustrates the storage requirements of the blockchain algorithm for increasing numbers of users. Bitcoin and Ethereum and all other blockchain coins share the same storage requirements. The blockchain's size is always somewhere between the purple and pink lines. As you can see, these don't increase linearly with the number of users. They increase greater than linearly. This causes what we refer to as the scaling problem. A number of scaling solutions have been proposed for the blockchain algorithm. Lightning networks, an increase in block size or a dynamic block size, and sharding. Unfortunately, lightning networks such as Radian do not fix storage complexity. They may reduce the total number of transactions added to the blockchain by a constant factor, but will not change the long-term rate of growth of the blockchain. Increasing the block size or changing to a dynamic block size works for a little while to relieve the congestion from the network. However, the blockchain still continues to grow too quickly until miners or stakers cannot afford the hard drive space to continue mining block. This in turn causes fewer people to mine, and eventually the network becomes centralized in the hands of only a few miners who can then double spend. Sharding is an admirable goal, but is extremely non-trivial on a public untrusted network. To date, after over 5 years of academics and developers around the world working on this problem, a working solution has not been found that uses sharding. Now let's look at Ripple's algorithm. Again, Alice wants to send some coins to Bob. Again, she signs a message saying that 100 of her coins will now belong to Bob, and enters it this time into the Ripple network. The Ripple network checks the signature on the transaction and applies the transaction to the Ripple ledger. The ledger is just a list of accounts on the network with the current balance for each account. When the accounts are updated, the transactions that caused the updates are discarded by the network, and only the new balance is kept. This is quite a good solution because it means that Ripple scales linearly. For every user added to the network, a constant amount of data is added to the distributed ledger. Again, only the account balances and not the entire history of transactions is kept. This solves the scaling problem that the blockchain algorithm suffers from. In addition to scaling linearly, the Ripple algorithm is also incredibly fast. It manages to be fast because the nodes work together cooperatively in order to validate transactions rather than working competitively to win coins by mining or staking, as in the blockchain. This ends up being a lot more efficient, and Ripple transactions take approximately 3.5 seconds to confirm, even under high load. Okay, but what about throughput? How does Ripple do in terms of throughput? Well, on-chain, Bitcoin can process approximately 3.5 transactions per second. Ethereum can process approximately 15 transactions per second. Ripple can process upwards of 1,000 transactions per second. Finally, let's talk about future-proofing. Ripple's algorithm can be expanded to process more than 1,000 transactions per second quite easily. The only limit on speed is the physical latency between Ripple nodes. Bitcoin and Ethereum will struggle to scale not just because their algorithms have nonlinear space complexity, but also because the miners or stakers in these coins are competitive rather than cooperative. Rolling out updates on these networks is tough and can cause chain forks, whereas Ripple is cooperatively designed and the only reward for running a node is that you get direct access to the Ripple network. Therefore, there is a positive incentive to continually update your Ripple node, making it easier to roll out updates. Well, that's it for part 1. Next time we'll discuss the business fundamentals of Ripple, including the outdated banking network that they are aiming to replace and the 150 banks they have on board. Stay tuned and thanks for watching.